concentrating on your videos here and not looking at this.
How much?
Okay, right. Now, in you've got generation, power generation, and you've got motoring. Right. Now, in a motor, you've got a rotor and you've got a stator, whichever way it stands. Right. Let's look at power generation at this stage. So if you got a permanent magnet motor, that means this is neutral, I mean north and south pole, right? And that means you got magnetic fields around this because it's a permanent magnet motor. And you then start forcing the shaft to turn on the other hand. So once you start forcing the shaft to turn, which basically you're turning the rotor, the magnetic field produced by the permanent magnet starts cutting the stator windings. Right? Now this generates power.
Was it in order?
Right.
Yeah, it's in order. Same color coding.
It's in order.
Whereby if in
Okay, let's see.
in
Number
Number
our
1,
case,
number 2, number 3, because it's written like that. They're all black wires. Number 1 terminal, top bottom.
which
Number
maybe
2
we should
terminal,
go
top
that side.
bottom.
What we do is put the run signal from the switch.
Which in our case now,
Which one will the run signal?
which in our case, we do not have a permanent magnet motor, right? We have a motor that's got a rotor. Obviously, it's just a squirrel cage motor. But the only thing why I would relate this motor, which is not permanent magnet, to this one, is because when the thing is running, this is already energized. When this motor is running, remember it's a fan, you want it to motor. So that is why it's already energized, meaning it's already got a magnetic field in that thing.
But this will be energized because of the
Yes, because yeah, the drive is firing onto these
power
windings.
here.
Yeah, so
That's inducing the rotor.
yeah, induces the magnetic field in the rotor. It's a squirrel cage motor, so that is what happens, right? Which when the drive starts up and it ramps up, that is, it is changing the frequency on these windings, and you actually, that is what we would call motoring.
Okay.
Right? Now you're consuming the power from the drive to here. Whereby on a permanent magnet motor, if I was to turn the shaft, I would not be, if I was to mechanically turn the shaft, force it, I would be generating the energy. You understand? Back into the system. Yeah. But now in this particular system, you've got the separator sitting here, and then you've got your big main fan. Now, if your separator sits here, that's the small 160 kilowatts, I think, into this ducting here. That's what you got. That's what your system is. And I think this is what, 700 kilowatts.
Say 700.
So let me just, for explanation sake, it's 700 kilowatts, and it's a bigger fan. So when this thing starts turning, it causes a vacuum here. Draft, which you call it draft. That draft then starts forcing this to spin
Faster than the set.
faster than the set point. So if I've got a set point here of
650 RPM.
650 RPMs, and I've got a set point here of 800 RPMs. 800 RPMs, I'm just making an example, 800 RPMs. Because of that, the drive will try and control this thing will ramp it up to 650. But then because of the draft, it will be further forced higher to run at, let's say, 800 RPM at the same speed as the main fan.
Okay.
So now you get a situation whereby the set point is sitting here, but then this is 0. So this is your set point, but then the actual is sitting here with a difference of 150 RPM. So the drive now, or this drive always wants to control the set point at, the speed at 650. So it tries and slows it down, but it cannot. because the draft is forcing it higher. Now, what situation do you then get? You get a situation whereby you are now generating. This is the motor, which is already energized, and you're telling it to run at 650 RPMs, but the motor turns at 800 RPMs. So that means you've got extra force onto this motor to turn it faster than by 150 RPMs. Now what happens? Because it's already energized, it acts like a permanent magnet motor. It now starts generating.
Okay.
You always move around 10 and 8.
Alright?
This cable you'll never found it down there.
Alright. Now it starts generating.
I only saw it today.
That power generated then goes back into the drive.
One of the cables that were small cables.
It goes back into the drive and affects the DC link voltage.
Through the same cables that's supplying it.
To the same cables that's supplying it, right? So after the rectifier, so you've got your let's call it the rectifier. You've got the rectifier. You've got your capacitors here. This is the drive now logic, and then you've got your inverter, which is IGBTs to say, right? So this is the rectifier. That's the capacitors, which is the DC link plus and minus. And then you've got your three phases out. Now that generation now comes from the motor side. This is where you connect the motor. Now you're generating from the motor to that backwards now. So what happens? This DC link starts increasing. Now a simple diode cannot take DC to AC. So in conventionally you would have to have resistors that would burn off the excess DC link. But if you put a resistor here, because this draft is continuous and you're always going to have excess DC, you will make a stove of the resistor bank. Basically, you will burn them out.
Just dissipate the heat.
Yeah, you won't be able to dissipate the heat and everything. So we can't put a braking resistor here. Now what we then did is that we removed this part here. We took it out. We put a rectifier, but this is a smart rectifier now. It's got diodes, just like the one that we removed, but then it's also got IGBTs, just like the inverter does. Right? Now the diode part is used specifically to make DC link voltage, just like we did with the other sequence. Now this makes DC link voltage. This is now powered, it's called DC link voltage. The inverter starts inverting and turns the motor. Your system starts turning the motor faster than required. It starts generating DC and increasing the DC link voltage. Once the DC link voltage is increased to two high levels, say the set point is 900 volts, right? 900 volts.
That's on your DC link.
On the DC link, and then your sequence now starts generating more voltage, and we're sitting at 1,100 volts of DC. What is the difference here? 200. That 200 volts is going to be fired back into the system through these IGBTs. Through these IGBTs is going to be fired back into the system. So this is going to be permanently working to fire this 200 volts X. Anything above 900 volts to be inverted back into the system.
Back to the grid.
Back to the grid.
Saving your power and money.
So you're now no longer wasting energy with conventional systems whereby any excess you'll have to burn to resistors. You're actually feeding it back into the grid. Makes sense?
Makes sense.